the presentation?
Yes, we can.
Thank you. Thank you for inviting me actually to speak on the Hitachi Energy field-proven grid-forming virtual synchronous machine. I've been following the UNIFI seminars, and I'm actually very pleased to be presenting here. And I'm looking forward to the questions and discussions at the end of the presentation. So I thought at the beginning I can just provide a very quick overview of the topics I'm going to talk about today. Although I guess most of you know about Hitachi Energy, I thought I may provide a very quick introduction of who we are today as Hitachi Energy and what our global footprint is. As the title of presentation says, the focus will be on grid forming technology. I will explain what the technology is in Hitachi Energy, where does it come from, and how it has been used. I selected two project references, which I believe provide are good examples of capabilities of this technology, but we have also some other projects that I will quickly introduce, and if there are any questions later, I can also discuss in more details. At the end, I will share some of the lessons learned from those projects, and I will share also our view on the capability of this technology and where do we believe we can stand if we, of course, work together on this topic in the future as well. So Hitachi Energy, it's for those who don't know, this is a joint venture between Japanese technology provider Hitachi and what ABB Power Grid division was. We are working on developing technologies to cope with this ongoing energy transition, to solve the challenges it brings. And we do so across different geographies and by serving different customers. They vary from utilities, industries, as well as transport and infrastructure. Our offering consists of product, system services, software and automation. But within Grid Edge Solutions, we like to say that more than everything, we provide solution to our customers because we configure and parameterize this multi-level, multi-layer battery energy storage control to fit best the use case and meet customer requirements. We are around 40,000 employees within Hitachi Energy, and we are divided into 4 different business units. The solution and the technology that I'm going to talk about today, the technology has been developed by Grid Edge Solution team, which is a global product group within Grid Automation business unit. We have around 2,000 engineers and science in R&D, so working very intensively on all those challenging topics of today. As we all know, the ongoing energy transition really refers to the energy shift from fossil fuel-based energy production and consumption to renewable energy generation. When it comes to energy transition, there are 2 main topics, and one of them is the need to replace synchronous generators, and the numbers that you can see here on the slides are the numbers coming from AEMO, Australian Electricity Market Operator, which say that there will be need to replace 14 gigawatts of synchronous generators in the next 8 years. In addition to that, the renewable generation capacity will at least double every decade from now to 2050. These numbers, what we noticed actually that these forecasts from AEMO are not always good, and they are not good because the transition is actually happening at even faster pace. So the question is really what will be the alternative technology which will be capable of providing the same services that have been traditionally provided by synchronous generators. And this is something which we really focus on within the group and Hitachi Energy. What are those services that are required to operate a stable and secure grid? And we think these slides represent quite well those. If you look at them from with wider picture, the most straightforward would be voltage regulation and frequency regulation, and then on top of that, fast frequency regulation. These are services that can be provided by different technologies, including also battery energy storage, grid following. The services that we are particularly focused on and interested are those that are shown on the upper half of this circle, and they are inertia, fault current, and system strength. Fault current is perhaps discussed more in the context of distribution network, and the question is really about what is the amount of the additional fault current that is needed or required from inverters. Inertia and system strength are other two services that today can be provided together with all other services by grid forming battery energy system. And in the next slide, we will see some of real world examples and how with our technology we did so. As I said, we've been working on this topic for quite some time now. And we started in 1988 in the company which was called Power Corp. And although the company actually has changed the ownership, so from Power Corp became ABB in 2011, and Hitachi ABB 3 years ago, and then finally Hitachi Energy since 2021, the focus has always been the same. So developing or maintaining power grid to operate in a safe and secure way, while also supporting a share of increased share of renewable energy sources. The business has started around microgrids and off-grid systems, and then has evolved into relatively high battery energy storage system in terms of the power and energy rating. And one of the examples is this Darwin Catron battery energy storage system that is under commissioning right now in Australia. Technology evolved from, as I said, solving power system stability rather than energy conversion. But what is really also interesting to notice is this transition from pure power application, or from a customer request to provide pure power application towards now more energy applications, and consequently also a larger or longer duration of the in terms of energy capacity. Although I mostly mentioned those project references in Australia, I think it's also important to highlight that we have actually a global footprint. All our projects and battery energy storage system installations worldwide can operate in both grid following and grid forming. Australia is the market which required grid forming operation first, or was the first region which actually experienced problems in terms of system stability, but we see a similar trend or requests coming also from other parts of the world, including Europe and North America. I would say that at least almost 50% of our deployments today operate either temporary or continuously in grid forming operation. As I said at the beginning of presentation, battery energy storage system control system is multi-level. It's quite complex, and in Hitachi Energy, it consists of different control loops or control layers. But these slides represent our primary control, so it is control that is implemented at a power conversion system. So grid following is current source inverters, which operates by locking onto the grid by mechanism called phase loop, and it pushes current into the grid to provide energy as a service. This control is mostly used in the context of grid-connected systems. It operates quite well and stable when the network is strong, but it has some challenges in context of the weak network conditions, because it relies on PLL, and then the system might experience problems with synchronization to the network when the network is weak. To overcome those problems or challenges, we developed grid forming. Grid forming is voltage source inverters, which provide voltage and frequency references, and the current is defined by the loads or the fault. This operation or this control mode enables good operation in context of off-grid system, but has some challenges when operates parallel with other generators. To overcome that challenge, we added on top of grid forming voltage source inverters a virtual synchronous machine. This is the software solution which emulates the behavior of the synchronous generator. So the algorithm consists of 4 different blocks: frequency governor, virtual inertia, automatic voltage regulator, and rotor flux model, and provides or ensures a stable operation in parallel with other generators. What is also important to highlight here is the capability of virtual synchronous machine grid forming best to operate to provide more than one services. So it can provide inertia, for example, when battery energy storage system is discharging, and this is really when this value stacking comes into it becomes important. So really the key to stabilizing grids and unlocking new revenue streams is digital automation as well as smart controls which are applied to grid forming converters. Ultimately, the idea is not only to replicate the capability of synchronous generators, but also to see how we can configure this algorithm to provide, if possible, even more services that synchronous generator can do today. So we have proven that all these services can be provided by battery energy storage system, and but the question is really, are they generating values to the customers? In sense, are they all monetized today? This slide really represents the situation again in Australia, where we can see that 3 out of 7 services today are monetized. Some others are under discussion today, and will be monetized in the near future. But this is really something that in this industry we will need to work together to enable and support larger deployment of this technology. Another slide really demonstrating or showing the technology that we've been developing within Hitachi Energy. This is IMESH portfolio. IMESH is the name of portfolio we in Grid Edge Solution are working on. It consists of 3 different product lines, which we call power, automation, and digital. Each of those product lines then add additional value in the when providing a solution to the customer. So the core of our portfolio is IMESH Power Store. IMESH Power Store is a smart battery energy storage system which can be configured and parameterized to meet different customer requirements. Here we are talking at power part of power product line. We are talking about primary control level, so the control that is deployed and at the power conversion system. On top of that, we have the automation. Automation enable seamless integration of battery energy storage system with other generators in the network. Those might be traditional or renewable generators, and more recently we see also EV charging assets. Here we are talking about both power management system as well as energy management system that then is about creating some additional economical benefit to the customers. On top of that, we have a digital product line. This is really about cloud-based data-driven services to support or enable advanced services or aggregate those assets to enable trading in the context of a larger energy market. What we really, the message that we really like to, send is that we look at our portfolio as in a way that each product line creates additional benefit, and then all together create values to the customer. Now I will move to the project examples, which I believe will then provide you with some inputs into the technology and how these systems actually operate. So the first project reference is ESCRI. ESCRI is the first grid-connected virtual synchronous machine in the NEM and perhaps in the world. As you can see here, Hitachi Energy has over 200 MVA of the VSM grid-forming battery energy storage systems operating or in construction since 2014. Some of the project references you can see on this slide. The first the first VSM connected to the NEM was deployed back in 2014. It is AusNet, a relatively small size of the battery energy storage system. If we look from today's perspective, it is 1 MVA, 1 megawatt hour system, which was targeting seamless transition of the distribution network. Another important and good reference project is Alinta. It is significantly higher in terms of the power rating. It is 35 MVA, 8 megawatt hour system. It has been in operation since 2017, and the main function of this system is to provide a spinning reserve. So this mine is capable of operating for 15 minutes, operating based on the power from the microgrid, and this is exactly the time that is needed for gas generator to start on, and in that case the continuous operation has been enabled. ESCRI is yet another project. It is 30 MVA 8 megawatt-hour system, a really good reference project which was playing an important role in Australia and helped national electricity market overcome some of the challenges in terms of stability of the network, and then providing all additional services that grid forming BESS is capable of. The last one I want to mention here is TGen, the project you can see on the north of Australia. It's 35 MVA, 35 megawatt-hour system, which is under commissioning right now, and will provide all those services such as inertia, system strength, but also but the customer is also looking into benefiting from 1 hour energy capacity to also provide some additional energy services. What we can also see here is really, as I said earlier, the evolution from power application, so a relatively short duration of the battery energy storage system towards 1 to 2 hour duration of the BESS system. So let me now go into more details of ESCRI operation. ESCRI is today the world's largest autonomous microgrid. The customer success story is really benefit of multi-stakeholder value stacking, and here this is really a good example of benefits provided by eMesh power store and eMesh automation. The challenge and the main requirement or request from the customer was for battery energy storage system to improve the reliability of supply in the lower peninsula, which was prone to lightning strikes, while at the same time supporting the integration of renewables. In this case, battery energy storage system is installed close to wind farm, as you will see in the next slide. The challenges were overcome by virtual synchronous machine, battery energy storage system, power store, which proved its capability to stabilize the electricity grid and then seamlessly island this region to enhance reliability and utilize local wind power. There are also some quantified benefits which customer achieved during this period. So they informed about reduced outages from 8 hours to 30 minutes for first 6 months of operation, and also return of investment was within 3 years. So really an impressive achievement, and the reference project we are also sharing with the customers worldwide that are interested in deploying these kind of systems to solve their own problems. So a little bit more details, and you can see actually here where the battery energy storage system is installed. So it is installed at the end of this long single supply line in close proximity to 90 megawatt wind farm. It is connected to the 33 kV network, and this area suffered quite frequent lightning strikes. So the requirement from the customer was that in case of the fault at the upstream network, the system needs to island and continue supplying the local loads and continue operation, seamless operation and integration with renewable energies, in this case wind farm, as said before. But when connected to the network, then the system can provide additional inertia and can inject active power within very short time. In addition to providing these technical benefits, the customer also benefit in terms of or gain some commercial benefits by participating to the wholesale market. So this is a kind of single line diagram of this part of the network. So you can see that S3 is connected to the 33 kV network and supplies the loads. Loads are some PV. There is a small town, and the maximum load power or the peak power is 8 megawatt. Then during the commissioning, this unplanned islanding was demonstrated. So at instant 1, this breaker at 133 kV breaker at the upstream substation opened. At that so in this first case, the wind farm was offline. I think important to mention. So there was SP was running unloaded, and at this first moment, when the breaker opened, BESS became the only grid forming source in now islanded microgrid, and instantaneously supplied the area. Some 80 milliseconds later, this protection system at the substation disconnected the upstream line, and S3 BESS continued supplying load. So we can see the voltage and current waveform here. So you can see that the robustness of the voltage waveform was actually demonstrated. There were no voltage shocks were experienced during this event of the seamless transition. What we can see here on the right side is that so BESS was running unloaded at the moment when the upstream breaker opened. This is the current that was supplied by battery energy storage system and was drawn by this 132 line. And at the moment when the protection system actually disconnected, the current then was defined by the this is in this way the seamless transition was demonstrated. What is again important to highlight here is that all the time in S3 the system is actually always running as a grid forming. So there was not any transition from grid following to grid forming and then vice versa. All the time system is operating in grid forming. The second event, which was also demonstrated during the commissioning time, was actually the case when a wind farm was connected. So please note the size of the wind farm. The output of the wind farm was 80 megawatt. Again, BESS was running unloaded to the NEM, and at this moment the local loads were around 4 megawatt. At the first moment, the 133 kV breaker at this upstream substation opened. BESS became the only grid forming source in the islanded microgrid. But at this moment, we had also the wind farm connected to the network. Some 80 milliseconds later, the protection system at the Rimple substation disconnected the upstream line, and at that moment, the 4 out of 5 collector groups inside the wind farm reduced the capacity of the wind farm by 80%, and you will see that on the next slide. So, as you can see here, as the frequency increased, the battery energy storage started charging. At that exact moment, the power rating of the wind farm was reduced to 20% of the nominal rating of the wind farm. So it was around 27 megawatts, which was below the power rating of the battery energy storage system. So battery system did not trip. at this moment, in this specific case, wind farm didn't ride through this event, and this was due to a very tight over frequency protection at the wind farm. So BEST actually started discharging and supplied the loads. Okay, the next demonstrated capability was the inertia response of the battery energy storage system. This was the real event, which when the South Australian state separated from the nearby state. So what we can see here is how the active power response mirror the rock-off event. What you can see shaded by red here is the positive rock-off, which resulted in the reduced active power output, while the gray shows the negative rock-off, then resulted in the increase of the active power. You can see here that the battery energy storage system was discharging at around 6 megawatt, and upon the disconnection of the interconnector between two states, which was followed by this positive rock-off event, the battery energy storage system actually immediately reduced the active power and then, as said before, mirror the rock-off event. What is important to show and notice here is that this inertia response is quite different to, for example, fast frequency response, because it does not rely on the measurement of the frequency, but provides an instantaneous response to the rock-off. And this can be seen even better on these slides, because these are measurements that were taken by high-speed data recorder. And you can see here that the current actually started decreasing below the frequency change, or the increase of the frequency was measured and detected by the control. Another important feature or capability of the battery energy storage system, which was demonstrated in ESCRI, was black start. Best, this was done by soft energization of battery energy storage system transformers and 33 kV network. So we can see on here that battery energy storage system ramped up voltage over 1 second time. This was done to avoid inrush currents of the transformer, 33 to 132 kV transformer. And what we can see here are PQ profiles when BEST picked up 33 kV load feeders in a consecutive manner.
Hey, Marija, just a quick time check, around 10 minutes left.
Okay, I will try to speed up because actually I have a couple of slides more. Together with Electranet, Electranet actually designed a system integrity protection scheme, which was designed to prevent South Australian system separation from the national electricity market. So a main requirement for BESS was to provide or to respond with 80% of the nominal power within 250 millisecond time upon receiving the trigger signal, and this was successfully demonstrated, as you can see here. The ESCRI project has been described in a couple of papers, including the application of advanced grid connected inverters in the NEM. This is a white paper published by AIMO in collaboration with Hitachi Energy, and S3 has really proven and demonstrated a range of valuable capabilities in the NEM, including island operation, system restart, connection of inverter-based resources in big grid areas, and provision of inertia. We are working with AIMO on exploring full potential of grid-connected, grid-forming inverters, and we have actually published together a paper which was presented in SIGRE last year, which was the intention was to understand what is an alternative technology to synchronous condenser, which can effectively damp voltage oscillation. So West Murray zone is part of the NEM, which is characterized as a weak network, and upon the fault, it was noticed the 0.9 per unit voltage oscillation. So the EMT model of PowerStore was integrated into the model of the network, and simulation was done considering 60 MVA synchronous condenser to understand the impact of connecting synchronous condenser of this size to reduce or damp this voltage oscillation. And as you can see here, it was proven that the voltage oscillation was actually damped quite efficiently. But what the main purpose, as I said, of the paper was also to explore an alternative technology, and in this case 60 MVA virtual synchronous machine was integrated, and the synchronous condenser was replaced by such a system. And in terms of providing system strength to the power system and damping voltage oscillation, it was proven that synchronous condenser and VSM battery energy storage system have the same capabilities. Then, of course, these two technologies are not directly equivalent, which makes a cost-benefit analysis more complex. This is another paper published in collaboration with AIMO, and if you are interested, you can look into the results. We have another project which I wish to share a couple of results with you. The PowerStore is deployed in Faroe Islands. SEV is Faroe Island utility, which set target to reach 100% of renewable energy in 2030. Obviously, they plan to do this by increasing the renewable generation capacity, and they mostly they base the production on wind farm. This island is 700 kilometers far from UK, Norway, and Ireland, so it's not connected to other power grids, and this so the energy is produced by the island. Here we deployed PowerStore battery system of 6 megawatt, 7.5 megawatt hour size, and as you can see here, other generators are solar PV wind. There are some diesel generators together with relatively small hydro plant, and synchronous condenser was installed at the same time when PowerStore battery system. EMesh control system is also a distributed control system was installed to ensure seamless operation of battery energy storage system with wind farm and rest of the network. As you can see here, battery energy storage system is installed in close proximity to the wind farm, but the rating of wind farm and battery energy storage system in this case is of a relatively similar size. Lessons learned from this project will now be used for deploying or installing another power store system, which is almost double in terms of power and energy capacity rating, and will be installed during this year at this larger island. You can see here very briefly, because of the time left, how this power grid actually evolved. The frequency was controlled in the island by droops and low share, and ISO control was managed manually by the operator with generator frequency set point increase or decrease. The customer informed us that at the moment, so this was by end of 2021, beginning of 2022, upon the installation of this wind farm, they reported to have some oscillation issues with ISO control, and this was actually overcome by integration of 6 megawatt battery energy storage system. So as you can see here, both Synchron and battery energy storage system were added to this feeder here. These are some, sorry, maybe the quality of the figure is not the best, but we have only limited number of recordings, as this system is in operation only a couple of months from now, but the customer is quite happy with the maintenance or with the frequency being regulated by a battery energy storage system. Also in this case, power store operates always as a grid forming best, and you can see here that actually at the moment when both thermal generators and hydro power was off, and how battery energy storage system support frequency control in case of unstable wind generation. As you can see here, there is actually no contribution from Synchronous condenser to keep frequency stable or around nominal frequency, in this case 50 Hertz. This is a real network event which happened on January 13, 2023. You can see how the wind power actually dropped from around 5 megawatt. At this moment, the wind, the energy, it was only wind power plant which was in operation, and the power actually dropped from around 5 megawatt to 0, and you can see here an inherent and immediate response from the battery energy storage system, and how battery energy grid forming best maintained frequency and provided stable operation in quite short time. And within 2 minutes from this network event, the wind power was back to the nominal or rated value.
Marija, if you could wrap up in a minute or two, that would be great.
Okay, so very briefly to mention that we have two big battery energy storage grid forming system under commissioning now in Australia. One of them targets to replace gas turbines for spinning reserve with VSM, and the control is managed by image control and SCADA. A similar functionalities will be provided also for a Rio Tinto project. Again, relatively high project, or quite high power rating, 45 megawatt, 12 megawatt hours, and we are looking forward into being able to discuss and present results and recording from these two projects in the next months. So to conclude on this, I would like to share some of the lessons learned from this project. Definitely the regulatory environment plays a large role and it's important to understand what are the services that BESS needs to provide and how those will be monetized. Very important from the operation point of view is actually where the asset would be sited, what is the system strength, what are the loads, as well as environmental conditions. The grid code requirements have to be understood. The experience has shown that the connection processes are quite long today, and understanding and applying proper requirements to the battery energy storage system has been a challenge in some areas or markets today. Simulation studies are required to assess and compare the capabilities of different technologies to provide system strength services, and early engagement is really crucial to understand the needs of the system and see how we can configure the system to provide the highest value. Finally, we can conclude that virtual synchronous machine grid forming BESS is a proven technology to run grids on renewables. As you have seen, we have been successfully operating this kind of system for over a decade. Today, we installed the first Australian NEM-connected grid forming BESS back in 2014, and then first large-scale VSM was registered on the NEM in 2018. So this is not a new technology today, we believe, but we are really understanding different requirements and needs of different systems globally. We have many publications, and also some webinars are available, so you are invited to to download and look for more details on performance of these systems. Yeah, so that's all from my side. Sorry, Deepak, if I took a bit more time, but I'm now. I will try.
No problem.